Cool. All right. Now to actually get started. So welcome everybody. I'm Zach, TA for the class. This is my fourth review of the semester. Y'all know the deal. We're here today to talk about the final. If you look at any of the previous semesters, you'll see that they pretty much all have the same sort of structure. Okay, let me just pull up one of the past semesters real quick. If I'm not mistaken, it's typically about 10 questions. Okay, it's not necessarily evenly weighted for like exams 1, 2, 3, and this one. Okay, it's not going to be 25% for each. I'd probably estimate it to be more heavy on the second half of the class, just because to even answer a question on an eigenvalue, you need to be able to find a null space. You need to be able to find a determinant, right? So that's asking the stuff you were asked on midterm 2 through a later question, okay? So they're usually 10 questions. The last one, you look at pretty much any practice exam or past exam, the last one's going to be least squares. Always least squares. One before that is usually some kind of stochastic or eigenvalues problem or something like that. And again, you should expect more of those like CDC inverse, eigenvalues, basis for this space, construct this, do that. That sort of general bigger problem is what you should expect for most of these questions. Usually, I think it's 2 pages of true or false. Okay, 1 page of true or false, but there's usually about 10 of them. And then pages 2 and 3, some short answer, some kind of like, does this exist? Does this not exist? Can you do this? Provide an example, that sort of stuff. So again, don't expect like one big question on find the column space of this matrix, right? You guys should be able to do that super quickly and super easily. That may be part A of a question, though. Then you have part B and part C and so on, okay? Okay. So this one is obviously a little bit different than the past midterm reviews we've had. This is fair game for anything in the class. If you want to ask me what the hell is a column space or what is a span, what is a linear combination, why do we call linear algebra linear, why do we talk about subspaces, anything like that. So what questions do we have? Yeah. Practice final A, problem 3C. One at a time, in priority. What's the priority of those? 6B? Okay, let me pull that one up. Did he already post the solutions to these? No. Don't do that. Yeah, there is something that you can definitely Google. So 6B you said, right? Okay. ChatGPT can't do a lot of things. Okay. One thing I will say though is if you go to any of these websites that Dr. Jankowski has about a PDF, okay, you change your little cursor right before the .pdf, you put -solutions, and whoa, the PDF for those solutions pops up. Yeah. Little file that away for some future classes, you know, just in case. But yeah, so it's there, but it's not there, you know. Okay, I apologize. I was stalling because my iPad was loading, or it wasn't responding at least. Is this the right question? Is this the right one? Cool. Okay. Suppose the matrix for the orthogonal projection onto the subspace W, which of the following must be true? Okay, well, this is the space W, okay? All right. And it's defined by this equation with 3 variables. What does this equation look like? Well, it's equal to 0, so what does it look like? A null space, right? So we can rewrite this space as the null, but this is an equation. How do we have to change this to a matrix now? So it's the null space of 2, -1, -1. Okay? So this is what W is equal to, okay? So what A is describing is the orthogonal projection onto this space, okay? So something that is on the space does not get changed. Something that is sticking straight off of the space will get flattened to 0. They're sticking straight off, right? Think if you have like a plane and you have a line sticking straight off, if we're projecting onto that space, we're flattening it down, okay? So just to talk about what that sort of looks like is I'll draw it out here. We have a line, and we're projecting something that looks like this onto this line. Another way they get asked this is find the closest point on the line W to Y. Okay, and that will always just be the projection. And this is y sub w. Okay, then this is y sub w perp, which just means the direction's taking off. Okay, so what this first question is asking is when we plug this vector in, when we project this vector onto this plane, are we going to stick straight off, or what's going to happen? So there's a few different ways we can do this. Okay. One way is we can just plug it in. Okay. So if we plug it into this equation, will this be true? Well, we're going to have x1 is 1, x2 is 1, x3 is 1. So is this equation true? Yes, right? So what does that tell me this vector is with respect to the space? It is in the space, okay? We are projecting onto the space, and we're already in the space. What happens? Nothing, right? We're already on our line. It's like if I give you instead, if this is y instead, what happens when I move, when I find the closest point to that line on the black line? Nothing. It's the same point. Okay, so this one is false. 1 second. All right, the second one says a squared is equal to a. So how can we describe a squared like verbally? What does that mean to do a squared? Well, what it means is to project and then project a second time. Okay, if I project and then I project a second time, does the second time actually do anything? No. We've already flattened onto that space. What happens if we flatten on again? Nothing. We're already there, right? So this one is going to be true. Doing a projection once is the same as doing it twice, is the same as doing it 3 times, the same as doing it 10 infinity times. Okay, it's going to be the same thing. The last one we're describing here is the eigenvalues of this matrix A that describes W. Well, A describes a projection. So what must the eigenvalues of A be? 0 and 1, right? Cool. Did you have any? Yeah. Yes. That would be what would be correct in this case. Cool. All right. Other questions? Any questions on this? What was what? I is wrong because what this is essentially talking about is if we have the vector 1, 1, 1 and we project it onto this plane, does it get flattened? Does it stay the same? Does it get changed? What happens? Okay. And what we find out is with the only information we're given is we can plug this vector in here, right? And we'll get 2 times 1 minus 1 times 1 minus 1 times 1. So it tells me that 0 is equal to 0, right? It satisfies this condition, which is what we define to be inside of W. That's what the space is, okay? So we're in W, and the matrix A describes projecting into W. We're already there. So nothing happens. So it's not equal to this. What it would be equal to is just 1, 1, 1. Okay. A second way you can solve this, it's a little bit more mathematic. We find a basis for W. Okay. To do that's not hard, right? We row reduce this matrix. We get 1, negative 1/2, negative 1/2. Okay. Which gives me the x vector is equal to 1/2, 1, 0, x2 plus 1/2, 0, 1. And what we can find is, can we get this vector from the basis created by these two vectors? Yeah, you can just add them together. It's another way of seeing that it's in the same space. Yeah. Because we're describing a projection, and projections are always 0 and 1. Okay. So again, the way you could see that with a little bit more vectors is you could see if these are linear common, or if these create this vector by a linear combination. Okay. Any other questions on this one? All right, other questions? Anything at all? I know, did you have other questions as well? 3C on the same one? Okay. 3C. This one? Cool. All right. This one says let A be a 5x4 matrix. First thing I do before I do anything else is I draw a 5x4 shape. Okay. For each x in R4, there is at most one vector y such that t of y. Oh, sorry. Back up. This one, the question just states that A is 5x4. Okay. Which of the following questions guarantee that t is 1 to 1? What does it mean to be 1 to 1? How can we find that in a matrix? Well, 1 to 1 is a pivot in each column. Okay. Right? So another way to say 1 to 1 is to have at most one solution for something. Okay. No y has multiple x's going to. That's what we define 1 to 1 as. So this first one, Ci, says for each x, there is at most one vector y such that t of x is equal to y. So at most one tells me how many free variables are they? 0. There's nothing with infinite solutions. Okay, so we have 0 free variables, so each column is a pivot. So is this one 1 to 1? Each column is a pivot? Yeah. Okay, the second one, for each y, there is at most one x. Oh, wait, I got myself backwards. Yes, I got myself backwards. Okay, I apologize. So these two are the ones that are meant to kind of confuse you, as they just confused me a little bit. But that's why we take our time during the final, and you have 2 hours and 50 minutes to answer 10 questions. Okay. So what this first one is asking is for each input, there's at least one output. What does that define? Nope. Nope. Yes, a function is like the actual way for it. Each x has a y at most. Okay. So this one just describes a function. That's why we have to be careful. The x and the y order reversing are what creates that onto and 1 to 1 thing. So that one is not true. But for the following one, for each y, there is at most one solution x, such that t of x equals y. So there is at most one solution. There are no free variables. We have a pivot in every column. We have linearly independent columns, which means that this is 1 to 1. Okay. Something about this matrix A that's 5x4. Can this thing ever be onto? No, because we're tall. The only kind of matrices that can be onto are wide and square, right? And only things that can be 1 to 1 are tall or square. So the last one says, or not the last one, the third question says, the set A of E1, A of E2, A of E3, and A of E4 are linearly independent. And E1, E2, E3, E4 define what we call the unit vectors. Okay? E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0. E3, 0, 0, 1. It's just where the 1 is in that vector. Okay. So if we have 4 vectors that are linearly independent in A, what does that tell me about A? Or what do these 4 vectors form with respect to A? A basis, right? We have 4 vectors for a 5x4 matrix that are linearly independent. Those are just our columns as well, right? A times E1 is just my first column. A times E2 is just my second column. And if they're all linearly independent, it's the same thing as saying they're all pivots. And if they're all pivots, it's the same thing as saying it's 1 to 1. Okay. Question 4. The homogeneous matrix equation AX equals 0 has only the trivial solution. Okay, if we have only the trivial solution, how many free variables do I have? What is the dimension of my null space? 0, right? I know it's late and I know it's a Monday, but you know. So what's the dimension of my column space? 4. What's my range with respect to my codomain? It's 4 space in R5. I don't really want you all to answer this every single time. I'm just trying to get you like the thought process of what these sort of questions ask and why there's like that connection between them all, okay? That's how like a true or false question would work. Given that AX has only the trivial solution, define the range in the codomain. Yeah. For this, in this particular case, it'd be none of them because it's tall. Just right off the bat, you don't even have to consider anything. Okay. So going back to part 4, we have only the trivial solutions, which means we have no free variables, which means we have 4 pivots. And if we have 4 pivots, that's 1 for each column, which guarantees that that's 1-to-1 as well. Cool? Any other questions on this one? Yeah. The first one is wrong is because it has x having at most 1 y. Okay. In this class, we talk about outputs having inputs, not inputs having outputs, if that kind of makes sense. So what this one is saying is for each x, there is a singular output or there's nothing. And of course, for each x we draw, it's going to go somewhere. Whether or not that place has a unique place defines 1-to-1, or whether or not we can get everywhere defines onto. But just knowing that x has a transformation doesn't tell us anything. It's just telling us we're working in linear algebra. And surprise, we're working in linear algebra. Right? Cool. All right, other questions? Yeah. How do we find eigenvalue and eigenspace? Okay. Ooh. So there's a few different ways to find eigenvalues. There's one that will always be true and one that will always get you the solution. Okay. The short form answer to that is if you're given a square matrix A, okay, the way to find your eigenvalues will always be solve the determinant of A minus lambda I equal to 0. And the solutions will always be your lambdas. Always, 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 and forever. Okay. For your eigenvectors, okay, it will always be the exact same thing. You must have a value to be able to find a vector. If you have a vector, it must correspond to a value. They go hand in hand, right? So to do this, we find a basis for the null space of A minus lambda I for each lambda. Okay? And whatever this basis is, it gives you your eigenvectors. Okay? And you list them out as linearly independent sets with respect to each value. Okay? There are some shortcuts. Okay? One of those shortcuts being the determinant of A will always be equal to the product of your lambdas. So what that capital pi means, it's the same thing as like the capital sigma you see in calculus. It just means multiply. So, for example, if my determinant of A is 0, what must one of my eigenvalues be? 0. Okay. Another little tricky thing that they may ask you is, given this matrix, tell me the dimension of the 0 eigenspace. 0 eigenspace has a different name that we've talked about since probably like the 3rd week of class. That's just the null space, right? Because you're looking for the 0 eigenspace that's looking for this, where lambda is 0. And you can see if we just plug in lambda equals 0, we just have null of A. Okay? So don't get confused if they ask you for the 0 eigenspace in a problem that you think has nothing to do with an eigenvalue. It's just another word for a null space. Okay? Another thing is your trace of A, which is adding the main diagonal, regardless of what shape your matrix is. It's always the same thing. Will always be equal to the sum of your lambdas. Okay? And this can give you a lot of shortcuts for things. For example, if it's 2x2 matrix, and my trace is equal to 5, and my determinant is equal to 6, what must my 2 eigenvalues be? Because it's a 2x2. 2 and 3, right? We're trying to find out what, in this case, if we had a 2x2A, so how many eigenvalues do we have total? If we have a 2x2 matrix, we always have 2. They might not be different, but they'll be there. For any n by n matrix, you'll always have n eigenvalues. Whether or not they're distinct remains to be seen. But for a 2x2 matrix in this case, we're going to have 2 eigenvalues. We know they have to multiply to 6 if I tell you that. And we know they have to add to 5 if I tell you that as well. And you can kind of just intuitively pull from that, oh, 3 and 2 multiply to 6 and add to 5. Those are my eigenvalues. You can just be done. You don't have to do any matrix math. Well, you have to do a determinant, but that's just algebra. Okay. Another like really easy example from that would be if we have Another 2 by 2 matrix, and the determinant is 0, and the trace is 50. My two eigenvalues are 0 and 50, right? Know that right off the bat. What two things multiply to be 0 and add to be 50? 0 and 50. Okay, just putting these two things together really quickly helps you with that. If it's not intuitive, you can still solve it out with the exact same process. These will never, ever, ever be wrong, okay? This determinant and this null space, they will never, ever be wrong. This is the definition of how these things are constructed, okay? And that means if these things are maybe not so straightforward, like what two things add to 2, or multiply to 2, and add to, I think of the best way to, and add to 0. No, I'm not going to try to do that on the spot. You can do complex eigenvalues with these if it's not super clear, okay? Yeah. Yes. So if it's not invertible, what is its determinant? 0. If we have a determinant of 0, what must one of our eigenvalues be? Yeah. And that tells me if I have an eigenvalue of 0, that tells me I have at least one free variable because I have a 0 eigenspace. I have a null space. So having an eigenvalue of 0 is the same thing as saying a determinant, saying you have a free variable, or saying you have a 0 eigenspace is the same thing as a null space. These things all go in a circle and mean exactly the same thing. Okay. Cool. Other questions? Yeah. What's a kernel? Are we talking about that in this class? Did that come up? Yeah, I don't think you need to know that. It's a cool thing. It's very applicable to a lot of different maths. We don't talk about that in this class. Yeah. Yeah, you. Yes, inverses and diagonalization are related. Okay. So the thing about inverses is a few things must be true, right? We talk about inverses in, I mean, it makes sense why we want an inverse, right? Like to undo something feels pretty fundamental, right? So talking about an inverse briefly, whenever we multiply something and we undo it, what is that the same thing as doing? Nothing, okay? So A times A inverse will always be I, which is the linear algebra equivalent of multiplying by 1, okay? So some things about A inverse, okay? If A is invertible, then A inverse exists, okay? For A inverse to exist, okay, we must determine if it's invertible, and we determine that with a determinant, which I'm going to abbreviate to determinant, to DET, because I forget how to spell it. So the determinant of A must be not equal to 1. Not equal to 0. What am I doing? Not equal to 0. Because if it's 0, that tells us we're not invertible, okay? If it's a number, it tells us it is invertible, okay? That's the whole idea. And what we get from that is if we are invertible, we have to be square. Our determinant has to be non-zero. We can't have 0 as an eigenvalue. All of our columns must be linearly independent. We must be onto. We must be 1 to 1. We must have a solution for one. We must have at least one solution for all y, and at most one solution for all y. Our range must equal our codomain. Our null space must only be the origin. The homogeneous system must only have the trivial solution. All of these things are the exact same statement. Okay? That whole thing I just listed, they're all the exact same thing. That's what a true or false question asks you. It asks you if you know what those things are related to. Okay? So I'm not going to list all of those things. It pretty much just boils down to this. Okay, determinant of A is not equal to 0. All right? And that tells me I don't have a lambda equal to 0. Okay? For A to be diagonalizable, okay? For us to be able to do a CDC inverse, okay? We want to talk about this again briefly. What we have is we have C and we have D, okay? C will be a matrix of our linearly independent eigenvectors, and D will be a diagonal matrix of our lambdas, okay? If A is n by n, how many eigenvalues will we always have? N, right? So we'll always be able to find D. D is never the problem child. We can always find a matrix D for any matrix. What we can't always find is a matrix C, okay? To find a matrix C, these matrices are n by n, And they must always be filled with eigenvalues all the way, okay? So one thing to note about that is all of our eigenvalues must be linearly independent, okay? Because if this matrix is filled with eigenvectors that are not independent, what is C inverse? Does it exist? No, because my columns are linearly dependent, right? So the whole problem with C is we're trying to find enough vectors to fill this space, okay? And what that may look like is if I have D that looks like this, okay? 3, 3, 3, 4, 5 are my eigenvalues. So I can ask you what the determinant is, and that's going to be 180, because you can just multiply your eigenvalues together. And then what we need to find is we need to find if we can fill C, okay? So for this question, every eigenvalue will always have an eigenvector. So 5 will always be able to fill this column. 4 will always be able to fill this column with an eigenvector, okay? And 3 will always be able to fill this column at least. What we don't know is if we can fill these two columns as well, okay? And to do that, we must find our eigenvectors by finding a basis of null of A minus 3i, and however many vectors we have, we plug them in here. If it doesn't fill up as many columns as I have in D, then it's not diagonalizable, okay? So going back to kind of somewhat all of what I just set up in one little thing is all algebraic multiplicities equal each geometric. That's on E. Okay, and that's for each lambda, okay? In geometric multiplicity, if we remember back to what geometry is the study of shapes, which are vectors and spaces. So geometric multiplicity is how many vectors, linearly independent vectors I have. What's the dimension of that space for each eigenvalue? Algebraic multiplicity is how many times it shows up in my characteristic polynomial. So for this, in this particular case, 3 would have an algebraic multiplicity of 3. And if these couldn't be filled, it would have a geometric multiplicity of only 1. So you can kind of see why it makes sense that we want algebraic and geometric multiplicity to be equal. We want to be able to fill both of those matrices. So the only relation you can really make between these two things lies here. Okay. If we have an eigenvalue of 0 or not is the only thing that kind of ties into both of them. Okay. What that can be written as is if A is 3 by 3 and it has lambdas of 2 and 1 plus or minus 2i, okay? How many eigenvalues is this total? 3, and I gave you a 3 by 3 matrix, okay? And this is a bad example. 2 and 3, okay? And 3 is a multiplicity of 2, okay? Is a matrix with these eigenvalues invertible? Yes or no? Someone confident about it. Yes, why? What do we not have as an eigenvalue? 0, right? We have numbers. Numbers mean we're invertible. Okay, these numbers help us out here. They don't tell me everything about diagonalization, but they tell me something. They tell me what my D is, and they tell me if I can get close to filling C, but they don't tell me if I'm fully diagonalizable. Okay, so the only relation is with eigenvalues. Things can be one, things can be both, things can be neither. Okay, it's a good example of a question to ask of find one that's one but not the other. Yeah. How do you find an inverse? Okay, for a 2 by 2, it's easy. For anything bigger, we get a little sad, but then we can still do it. Alrighty. So to find an inverse of a 2 by 2, this is a really good example of something you'd see is like a part on one of these questions, okay? So another way that you can see why a determinant of 0 would not allow you to make something invertible is if A is 2 by 2, A, B, C, D, okay? Then this inverse is equal to 1 over the determinant of this matrix times dA, negative B, negative C. Somebody please correct me if I'm wrong. For a 2 by case, this is really, really easy. Looking at this, what do we not want this bottom thing in the denominator to be? What do we not want that number to be? So does that make sense why that defines invertibility, right? 1 over 0 explodes. We don't talk about that in this class. You can kind of apply that to higher dimensions, though there's not an easy way to consider that. There kind of is, but if you want, I can point you to the right Google page for it. If for a bigger matrix, like a 3 by 3, like you had in your previous midterm, what you're going to have is you're going to have matrix A, and we'll call this a 4 by 4A. Okay? What we can do from here, the first thing I would do is I would check if any of the columns or rows are similar, because then you know right off the bat if it is or is not invertible. Okay? That'd be a good little like half trick question, where to see if you know what you're doing or if you don't, or if you're just plugging in numbers. So to actually solve for an inverse, we invert it with I. So this is going to end up being a 4 by 8 matrix you have to row reduce. And if the columns of A are linearly independent, what does A row reduce to? The identity matrix. Okay? And then we'll have A inverse over here. If it is not invertible, you will not get the identity matrix over here. If you don't get that, it is not invertible. Okay? That's another way to see that that's true. Okay? Any other questions on this? Cool. Other questions? Yeah. If lambda equals 0, it is not invertible. And what that tells me is one of my positions in D is 0. It doesn't tell me anything else about diagonalization. It still could be diagonalizable. We don't know. We can't discount that it's not. Okay? But what it does tell us is one of those positions in D. And that's pretty much all it tells us. Can't really go further than that. Okay? Does that make sense? Yeah, in the black. Sure. Midterm to the actual midterm? The exam or the examination? Exam, you said 2, 4C. 4C. Also, I will make a comment on this because multiple people have been caught in this class before. For the love of God, y'all, don't risk your time at Georgia Tech with cheating. Just please don't. There's been instances in the past of obviously people getting caught for cheating. Take the 30 if you think you're going to fail, than taking the passing grade and cheating, because if you get caught, it will go on your record. You will fail the class. All kinds of stuff happens, and we don't like to come back from there. So just let this be a warning of whatever, because this is one of the examples where we had 2 versions of the exam, and people got caught with that. So on that note, here's this problem. So this one says, let V be the subspace of R4 consisting of all of the... Is this the right question? Okay. I apologize, I screenshotted too much. Let V be the subspace of R4 consisting of all vectors of the following form. Write a basis for V. Okay. So the way I would write this question now is I would look at this and I would recognize that this looks like a column space. Okay. We have a whole column. We have a set of equations. We don't know what they're equal to. That defines a column space, right? Trying to find out what they're equal to and find out the solutions from there to find what a linear space looks like. Okay. So we can rewrite this problem. Oh, that's too small. As -4, 0, 6, 1 times x4 plus 0, 1, 1, 0, x2. Okay? This is me separating these things out into 2 separate parts. Okay? And now what we have is any combination of these 2 vectors will be in our space. Will be a combination of them. Okay? So if any combination is of these 2 vectors form a basis. Okay? So this is just one where you have to recognize, pull it apart, see the vectors. Cool? Cool. Other questions? Yeah. 2A on this exam. Any particular part or all 3? Got it. Yeah. Okay. This is just the solution. I had to screenshot the wrong thing. 2a. Ah. I apologize. There's not a version of that answers on it. All right. So this question was written in two ways. Is this the way that you wanted to see it, x minus y? It was also written x, y in the other exam. Is this right? All right, cool. So what this question is asking is the three parts of a subspace. Does it contain 0? Does it contain the origin? Is it closed under addition? If we add two things in the space, do we stay in the space? Is it closed under multiplication? If we take anything in the space and multiply by any number, am I still in that space? Okay, the first one, easiest one to check. Does it contain the 0 vector? If we plug in 0 to first x minus y is greater than or equal to 0, is that true? Yes, right? Okay. The second one, is it closed under addition? Okay, there's a couple ways we can think about this. One of the ways that we can rewrite this is we can rewrite this as x greater than or equal to y. Okay. So if x is greater than or equal to y, and if I have u1 and u2 satisfy this, and v1 and v2 satisfy this. And what I mean by that is u1 is greater than or equal to u2, and v1 is greater than or equal to v2. I apologize for using similar looking letters, but I usually put a little tail on u. So what this question is asking, if we add these two together, does that still hold? Well, what that is u1 plus v1 and u2 plus v2. Okay? And this asks now, is u1 plus v1 greater than or equal to u2 plus v2? Yeah, because this is bigger than this, and this is bigger than this. So we have two bigger pieces we're adding together. And is that bigger than or equal to two smaller pieces that we're adding together? Yeah. Does that make sense? Okay. I'll draw this out graphically as well, but I'm going to go through the algebra of all three parts first. So part 2 is a yes. Part 3 is this closed under scalar multiplication? Okay. So let's go back to just this u1, u2. Okay. If I have u1, u2 and I multiply it by c, and I'm going to get cu1 greater than or equal to cu2. Is there an example of a c I could pick to make this no longer true? Yeah, what if it makes c negative 1? The most typical case that will be an exception is a negative. Okay. So if, for example, u1 was 2 and u2 was 1, we have 2 is greater than or equal to 1. But if we multiply both of those by a number, it's not still true. Okay, so that's why it is not closed under multiplication. Okay. Another way you can see this, and which is a fine way of solving it as well, okay, we could graph it. X is greater than or equal to y. This would be a graph that looks like this, greater than or equal to it. So it'd be this whole space here. Okay. Does this space contain the origin? Yes. If I add any two vectors that are pointing somewhere in this direction, if I add them together, will they stay on this half of the coordinate plane? Yes, you can kind of see that visually, right? There's no way if I add anything anywhere close to this that I can get to the other side. And note I'm saying addition and not subtraction, okay? But the counterpoint to that is if I have something that looks like this, could I multiply it by something and get it outside of the space? Yeah, we could flip its direction to a negative, and now we're outside of the space. This is a graphic representation of what a subspace means. It means to be these three things, okay? So the other version of the exam had the x times y greater than or equal to 0, okay? Was it equal to 0 or was it equal to 1? I think it was equal to 0. We'll just assume it's equal to 0, because that's what I've seen at the most typical case, okay? So if we were instead solving the other version of this exam, where it's x times y equals 0, okay? If I were to draw this on a space, okay, that means either x is 0 or y is 0, right? X times y equals 0. One of them has to be 0 for that to be true. So my space is the axes, right? X is y is up the y-axis, and y is 0 is the x-axis, right? So does this contain the origin? Sure does. If we add two vectors on here, will we stay on these lines? No. What could be the case if we add two things on the same line, they could stay on that line, but we have more to consider than that, okay? However, if I have something that is on this line and I multiply it by any number, will it stay on this line? Yes. This would be an example of something that is closed under multiplication, but not addition. The x minus y is greater than or equal to 0 is something that's under addition, but not multiplication. Okay? All right. Next question. Yeah. Yes. Vectors. That's the definition of a vector. That's the start of the origin. Well, okay. Technically, it just has a magnitude and direction. Despicable of me. But we always define it as starting from the origin. Okay? Yeah. Yeah. Okay. This is a big one. You should expect to be asked this. This also comes in the form of a least squares. Okay? There's like 5 different ways to find the closest vector. All right? If you're you'll always be given like a space W, right? You're given something that you're projecting onto, something that you have to be close to, right? Okay. There's a few. If you're just given like a matrix of W, what you can do is if you know what that space looks like, you can find yourself a C, D, C inverse diagonalization, right? It's a projection. You know that's true. You know what D is going to look like. You know how many 1s and 0s it's going to have. It's going to have as many 1s as it is dimension you're projecting onto. So if you're in 4D and you're projecting onto a 3 space, you're going to have 3 1s and 1 0. You have to find a basis for that space that W is, and that becomes the rest of your columns of C. And then from there, you can multiply out 3 4x4 matrices and finding the inverse of one of them. Not fun. So to list that out, one way to do it is to multiply CDC inverse times your y to get what we call YW. Okay. And what again that means is if I'm drawing and if I'm in 3 space, I have some plane, which I'll call W, and I have some vector that sticks off of the plane. Okay. There's going to be a point on this plane that's closest, right? Okay. And it will always stick straight out with a right angle. Okay, and we define these parts as YW, the part that's on the plane, and YW perp. Or you've heard the orthogonal component. Orthogonal just means perpendicular in a higher dimension. So that is what I'm like describing here, is to find the CDC inverse, a matrix that describes the projection onto a plane, matrix A, and multiplying it by Y, we get YW. That's from exam 3. That's not an impossible way to do it. You know how to do it. It just sucks. The second way to do it is if we set a matrix B, let me write over here. W equals the span of, I'll call it just V1, V2 in this case. All right, and for all of the ones for it, I'll talk about that as well. B, let's call it equal to V1, V2. Just a matrix with those as columns, okay? One way that we can find a matrix A that describes the projection is multiplying B times, I always mess this one up, B transpose B inverse B transpose. Can someone validate that? Or does anyone, if anyone can correct that, let me know. I always misplace where the T's go. So this can give us this matrix A as well. And then A times Y is equal to YW. This way is a headache, but you can do it. It's not impossible. Again, still a way to do it. Okay. Now to talk about the easier ways to do it. Okay. I'll talk about the special cases of projecting onto a line first. Okay. This one is something that will come up. I usually expect to see it on the final. It shows up in some form or another. Okay. If we're projecting a vector y onto a vector u, okay, so let me rewrite this as span of w, or sorry, span of u1 is equal to w. Okay, this is us projecting y onto that line. That is exactly what this is. Okay, but if we smash it down into a line projecting on a line, it'll always be the same thing. So we've talked about dot products before. You guys know what a dot product is computationally. But what a dot product describes is how much two things are pointing in the same direction. It's the definition of a dot product. Okay. If that number is positive, do you think they're pointing roughly in the same direction? Yeah, right? If you think it's negative, do you think they're pointing in the opposite direction? Okay. If you think it's 0, do you think they're pointing in directions that are totally unrelated to each other? Yes. Okay. So a way to visualize that first would be if I have a vector here and here, the dot product is going to be positive. Okay. If I have a vector here and here, it's going to be negative. If I have a vector here and a vector here, there's a right angle between them, it's going to be 0. That's how a dot product works. Okay? So again, a dot product is a measure of how parallel two things are, how perpendicular two things are. Same idea. And to find yw, it will always be u dot y over the magnitude of u squared times u. Always the exact same thing. Where what this basically boils down to is this is just some constant that we're multiplying u by to see where it is on this line spanned by u. Okay? Because the span of u is the same thing as saying any number multiplied by u. And we're finding what that particular number is in this case. You have a question about this? Okay, I'll get back to you then. That's one way to do it. A way to find the general matrix to find what this is it is u times u transpose, not dotted, this is multiplied, divided by the magnitude of u squared. Sure, yep. And this equals a matrix A. Maybe write this is equal to y w. Okay. And from here we get A times y equals y w. Okay. Two totally fair ways to do it. This would be the way to do it if they ask you find a general matrix for a projection onto the line. Okay. You can also do CDC inverse. You can also do this headache of a formula with the transposes. Still all fine. Okay. So that's projecting onto a line. Now let's talk about least squares. Least squares is how pretty much any curve fitter works. If you've used MATLAB and you've used any kind of like polyfit, you're just using the least squares. You don't have to, it's the same thing. So the way that this works is if we have a matrix, I'll call it A, is once again U1, U2, where W is equal to the span of U1, U2, okay? And we have a vector Y, and we're trying to get as close to Y as we can, okay? Well, if we were to write this out, A times some vector X is equal to Y, and this isn't something we can solve because it's inconsistent because Y isn't on that plane. Okay, Y isn't on that line. That's why we have to find a projection in most cases. Is to find the closest point or the closest solution to something. So this is all of this whole shebang of trying to solve a least squares is finding the closest consistent solution to an inconsistent system. Okay. So the way to do this is A in this case, let's call it like 4 by 2. This isn't something that is invertible. So without taking too much of what I'm saying at face value, the closest thing we can do to an inverse is a transpose. Okay? And we can solve this actually. We'll find A transpose A, augmented with A transpose, in some cases you can call it B or Y. Okay? And this will be a system you can solve. You're going to get the identity matrix augmented with what I'm going to call X tilde. Okay? It's a solution. Okay? And what this X tilde is in this case it would be 2-dimensional. Okay, but Y is a 4D vector. Okay, so that is not the closest point we can get because we're not It doesn't even make sense to talk about 2 points in a 4-dimensional space. So what this is where you would stop for a true least squares question. This is finding the m in the mx plus b equations. Finding the m, finding the b. That gets you as close as possible, okay? To find the actual projection, what you do is you plug in a times x tilde, okay? Because x tilde is the closest solution. So if we get the closest solution times the transformation, what we're going to get is we're going to get yw, the closest answer, or the closest output. The closest input yields the closest output. That kind of makes sense, right? Or it's the input that gets us the closest output. That's how we define and solve it, okay? So this is how you would take a least squares one step further and find a projection. If you're finding like curve fitting, you never go past here. You don't do this. You're asking to find the slope of a line, the equation for a line. Something else they can ask is they can ask for a more complicated equation. It doesn't have to be mx plus b. It can be ax squared plus bx plus c equals y. That's a fine way to solve a least squares problem. It's not hard or impossible. You know how to do it. Okay, it's just a 3x3 instead of a 2x2. Okay, yeah. The 4 points? Yeah, let me pull one up from a previous exam. Oh yeah, but these basically some of the ways that you can find a projection. Pick whichever one is your favorite and solve it that way. I like usually these last two. There are a couple more ways to do it if you want to look through your textbook and all of that, but these are the ones I'm focusing on for right now because I can't talk here for like 3 hours. Example practice final A. Alrighty. This is a very common example of what you would see on the last question of the final. And what I know students have usually done when they've prepared for this final appropriately is I usually see people just skip to page 10 and solve the least squares and move on because you know it's going to be there. Okay, you don't know it's going to be there, but using statistics, it's probably going to be there. I don't see the exam until y'all see the exam, so all I say is speculation anyway. But use least squares to find the best fit line, mx plus b, okay? Well, let's plug this in for each point. So for the first one, 0, 14, I'm going to rewrite y's over here because I don't know why y's out front. We're going to get m times 0 plus b equals 14. We're going to get 2m plus b equals -5. We're going to get 6m plus b equals -1. If we were to plot these points out, other way. You get something that looks like this, right? And it's pretty clear that there's not like a clean line we can draw between them. So that's why we use least squares, to find the line that is closest to them, okay? So what we can write out from here is we can write this as 0, 1, 2, 1, 6, 1 times mb equals 14, -5, -1. Okay, so always be the exact same, A transpose A, and if we transpose that, we're going to get, so we're solving A transpose A. And it's going to be 0, 0, 2, 6, 1, 1, 1, multiplied by 0, 2, 6, 1, 1, 1, augmented with 0, 2, 6, 1, 1, 1, by 14, -5, -1. And from here, we're going to get 4883 augmented with -16.8. Okay. So we have a system. Cool. Does this look like it has a solution? Should be able to look at this and tell me if it has a solution. Why? What can you tell me about the two columns? They're totally different, right? They're not the same by a scalar, right? So these two are not linear combinations of each other. So they're linearly independent. So in this case, the columns of A transpose A will give us the identity matrix when we row reduce. Okay, and we get the identity, or I guess I could write it out. It's only 2 by 2. And it's going to be -2 and 8. Okay, so what does this tell us? This is my x tilde, okay? And again, this is just what I call x tilde. You're not going to find that in like your textbook or anything. I think they call it something different. What is what? I just like writing tildes, so that's why I call it x tilde. But it means the input to get us closest to the output. Okay? And in this case, what our input is it's that line. It's the line of best fit. Okay, so what this tells me is we lined it up to be M and B. So the line of best fit is -2m. Oh, no, that is M. -2x plus 8 is equal to y, is the line that's closest. Okay, and this would be the exact setup that you should expect and be able to solve pretty quickly. Okay, any questions on this? All right, other questions? Does that work? I don't know how, I can't really see how clear it is up there, but okay, yeah. This one here. Would the x vector be an eigenvector? So we can't talk about eigenvalues because A isn't square. A was square. It wouldn't because it's the input to get us closest to the output. It's not the closest output, if that makes sense. Like x tilde isn't YW. It's the x to get us YW. Does that kind of make sense? Say that one more time. Yeah, so for this one, we're skipping the step of finding a general matrix of projection, and we're just getting straight to YW. A transpose A is not the matrix that describes a projection. Okay, so using that just kind of bypasses the whole like projection idea, and we just skip to getting as close as possible, if that makes sense. You can talk to me after if there's more, just because it's, yeah, cool. Yeah. Four on final exam, A or B? A, the whole thing? Just part A, got it. Okay. No, not a link. Oh, no, that's not it. All right. So it's a very common, like, do you understand what projections are in general sorts of question, okay? Match each matrix with its corresponding transformation, choosing from I through 1 to 8 by clearly writing that Roman numeral next to the matrix. Note that there are 3 matrices and 8 options, so not every matrix is used. Okay? So the way to kind of think about this is they're only going to ask you reflections, rotations, projections. Okay, those are pretty much the only like big ones they're going to ask about. Okay, or like a shear, but you wouldn't have to describe that shear in particular detail. So how we write a rotation in general is always the same. Cosine theta on the diagonal. Negative sine theta, sine theta. And this is for a counterclockwise rotation. Okay. If it's a clockwise rotation, we just set theta equal to a negative theta. That's just a negative angle instead, okay? And yes, you should remember the two big things that people forget that they need to know in college at Georgia Tech is you need to know the unit circle and you need to know the quadratic formula. You'd be amazed. So looking at these, which one of these looks the most like something that looks like this? The third one, right? Those look like a bunch of cosines and sines. 1/√2 is the same thing as √2/2. Okay. So looking at this matrix, we can say that the cosine is √2/2. And what angle does that happen at? Pi/4. So that narrows down to this one and this one. Okay. My negative is in the top right, which means my sign is down here, my positive sign if it's a counterclockwise. So it's a counterclockwise by pi/4. Oh, no, that's not how we write that. B. Okay. We don't have to answer these in order, but that's just the way that I like to look at these. Okay. So now looking at this, we can look at this top one as well in two different ways. Okay. Does this look like this general matrix here as well? Did you think of a cosine and sine to make this true? Of the same angle? Yeah. Like at 90 degrees, right? Cosine 0, sine 1. Okay. But in this case, the sign is -1. Okay. So what we can tell is this is a clockwise rotation because the positive is up here. So pi/2 is what these correlate to. So now is it clockwise or counterclockwise? Well, if it were counterclockwise, it would be 0, -1, 1, 0. Okay. But since it's clockwise, but since this is negative, it has to be clockwise. Okay. So this one is V, I. Okay. So that's just kind of how I look at these. I look for those opposite negatives on the minor diagonal. I look for the same number on the main diagonal. That tells me what a rotation would look like. Okay. The second one says the standard matrix for this. Okay. A way that you can think about this is if we multiply this by xy, what we're going to get is instead of xy, we're going to get yx, right? We multiply xy by that matrix. So what we're doing is we're flipping x and y, right? And what is that the same thing as doing? It's the same thing as reflecting across x equals y. Okay. Okay. So if we wanted to just talk about these as well, reflection across the x-axis, what this would look like is the x value is going to be unchanged, and the y value is going to be flipped. Okay. Another way that you can generally think of this is my first column will always describe what happens to x equals 1, y equals 0. My second column always describes what happens when x is 0 and y is 1. Okay. So if we want to just quickly make the matrices for all of these, it's not too hard. Reflection across the y-axis can be -1, 0, 0, 1. Okay. Reflection across y equals -x is going to be, that becomes -1, that becomes -1. And then these you can just plug into the general form for a rotation. Okay. Yeah. Yes. Sure. So let's say A is my projection matrix. Mm-hmm. Mm-hmm. Okay. What does null A represent? So there's a handful of equations that tie these all together, and I'm thinking of the easiest way to answer it without just going through all the equations. But those equations, I'm just going to write it out and talk about it for a moment. Okay. So what you're going to see is you're going to see the null of A is equal to the column of A. with a little box here and a little box here. You've seen these as 4 equations, okay? But they have row and the word row A instead, okay? And what I mean by all of this is in the blue boxes, one of them must be filled with a t, and in the red boxes, one of them must be filled with a perp, okay? So if we wanted to talk about, or for example, if the t was here, okay, then I would say the null space of A transpose is equal to the column space of what? Be the column space of A perp. Okay, that's how they would have to fit. Does that kind of make sense? You've seen this again as a set of 4 equations. I'm combining it all into one equation. Okay. So again, if you look at those sets of 4 equations, it's the null space of A is equal to the column space of A transpose perp. The column space of A perp is equal to, or sorry, the null space of A perp is equal to the column space of A transpose. The null space of A transpose perp is equal to the column space of A, and the null space of A perp is equal to the column space of A transpose. And what all that boils down to is, again, the same thing. So what null A would boil down to is null A has to be equal to the column space of A transpose, perp, okay. Column space of A transpose, row space of A. So, I'll get back to you on this one if you want to come up and talk to me after. I'm like 90% sure that this is, if we this will give me W perp, but what we define W perp as, the matrix of null A. What do you mean the matrix of null A? Null A only gives us a vector, right?
Yeah, like vectors like.
Okay, so what this would look like is the null space. So what we define W perp as is always the column space of A perp, okay, which is equal to the null of A transpose, okay? So these 3 go together. What I'm just trying to remember is if for a projection, is the column space of A transpose and the column space of A the same? That's what I can't remember, and that is a very niche thing. So I'm not going to answer that because I don't want to be incorrect and say something wrong, okay? I think that's a very specific thing that you shouldn't, worry too much about. Yeah. Yeah, so row space would be like if this was my T and this is my perp. Let me write that in black. So if this is the box that fills the T, so if this one has a T, this one can't have a T. If this one has a perp, this one can't have a perp, okay? So that's me writing the column space of A transpose, which is the same thing as row of A. I just hate writing row because I think it doesn't make much sense to think about. Okay, does that make sense? It's just tying those together. Anytime you see a column space of A transpose, that's just the abbreviation for row. Yeah. Yeah, steady state. Any more questions on this stuff? Yeah. Okay. Null space of B is W perp. Okay. What was that? Say that one more time. That's what I cannot immediately remember. I can't remember that fact about projection matrices.
But it was a fact.
That was a fact? Okay. Okay, then we'll just take that at face value then. Okay. So then if this is true, if the column space of A transpose is the same as column of A, and column A transpose is the same as column of A perp, which we define as W perp. Okay, that's how we define what an orthogonal space is. What W perp is it's the line sticking off the plane. Okay, if we're projecting onto a plane. All right. So you want to know why this equation is true? Or were we just... Yeah, okay. I don't think it hurts. It only takes a second for me to explain. Okay. So let's let a matrix B be the vectors that construct W. Okay. So far, so good. So what we have is we're looking for some W to be orthogonal to U1 and U2 to construct W perp. Okay. So what I want is I want U1 dotted with W to be equal to 0, and I want U2 dotted with W to be 0. So what this will give me is it'll give me U1 W1 plus U2 W2 plus U3 W3. Call that 1, 1, 1, 2, and 1, 3 equals 0, and we'll have U21 W1 plus U22 W2 plus U23 W3 equals 0. And U1, U2, and these numbers are just the entries in U. Okay, it's my first entry in U1, my first entry in U2, and so on and so forth. Okay, we want this to be true, and we know what all of my entries in U are. Okay, so this looks like a null space. Okay, it looks like a null space of U11, U12, and you can fill out the rest of the matrix from there. Okay. So that's why finding the null of this space, or finding the solutions to this equation, which is just finding when those dot products are equal to 0, gives me W perp. Yeah, that's why the equation is true. Okay, cool. I'm glad. All right, cool. Any other questions on this? Okay, let's go back to the steady state stuff. Steady state vectors. So to talk about it, we got to talk about stochastic matrices, all right? Stochastic matrices are just, you now are using linear algebra for statistics. That's fine. That's something that is very commonly used for. So stochastic matrix. So some facts about it. Every entry equals probabilities, okay, in decimal. And what that means is they must be somewhere between 0 and 1, okay? Each column must sum to 1. Each column must sum to 100%. Probabilities. This makes sense. Another fact is you will always have a lambda equal to 1. We don't need to spend too much time on why that is, but it will always exist. And the one eigenspace will always be a line. Okay? These are the three biggest facts I would say about stochastic matrices. Okay? Positive stochastic matrices, which is what we talk about. So what this could look like is if we have, let me pull something up real quick. So if we have stochastic matrix A that looks like 0.7, 0.6 for my first row. Do I know what goes here? It's 2 by 2. What must it be? 0.3, and this one must be 0.4, because my columns have to sum to 100%, or the number 1. Okay? So what we do is we use this fact that lambda has a 1 eigenspace, or not lambda, A has a 1 eigenspace, which is a line, which is where we get our steady state vector, W, okay? And what that means is as we go to infinity, okay? How many of you have taken a calculus class before? Right, most Georgia Tech students. Do you remember these nice little vector maps? I forgot the exact word that people use for them, but what we have is if we're plotting the derivatives, we'll have something that looks like this, right? This isn't something you actually have to use. This is just something that I think is helpful to show and kind of move from here, okay? What a steady state is if we start at any point anywhere on this graph, we're going to follow this and approach that line. Anywhere. If we start anywhere on this map, we'll always end up approaching that line, okay? Even like here. or way, 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 way down in the bottom of wherever, it'll always eventually come up and approach that line, in this case. For those of you that have to take diffie-qs and groaned, God help you. You will be drawing these in diffie-qs, and they will be more complicated than that. But it is what it is. So that's the idea of what a steady state is. It's the thing we approach as eventually things converge as time goes on, okay? So what does A times some vector represent? Okay, well, V represents where we are, and A is what happens when we transform by some unit time or by some process. Okay, maybe I press a button and things move to some extent. Maybe every day people go to different restaurants. Okay, the way we can write a stochastic matrix, and the way I always like to do it, is I always draw this little line here, and I draw this as start, and I draw this as stop. Okay, this is my A and B, and this is my A and B. Okay, so what this number represents is 70 people that start in A, end in A. 30% of people that start in A, end in B. 60% of people that start in B, end in A. 40% of people that start in B, end in B. Okay, that's how I read a stochastic matrix. And that's also how you construct one if you're given a word problem. Okay, you think of where do people start, and where do they end, and then that number corresponds in the matrix to it. Okay? So if we're wanting to find the behavior as A goes to infinity times any place we start, think of like this diagram here. We can start anywhere, and it will always approach the same line. Okay? A times B will always equal W. Okay? And what I'll call it is, I'll break this up into two parts. I'll call it N times W. All right? So how do we find this? Okay. What this looks like is if we sum up N, or sum up V, V is where people are as we begin. So maybe if in this particular case I give you that 80 people are starting going to A, or starting in A, and 130 people are starting in B, this is what my V would look like. Okay. And if we add these up, we're going to have 210 people total. That's what my N is. It's the total number of people. Doesn't matter where they're distributed at first, they're always going to end up in the same space. Equals N. And now what we have to do is we have to actually find the one eigenspace. It's not too hard for this case, right? We just subtract the identity matrix. We get negative 0.3 and 0.6. Does it matter what my second row is? Why? Because it just kind of goes away. You're right, but why? What is true of the determinant of this matrix? What must it be equal to if 1 is an eigenvalue? It must be equal to 0, right? If 1's an eigenvalue, A minus 1i, the determinant must be 0, right? The determinant 0, is it invertible? No. If it's not invertible, then my rows and my columns are similar to some extent, okay? So it's the same thing when we did complex eigenvalues. We can just kind of skip over them. Okay, we can use the exact same process. And I can get a vector from here that looks like 0.6, negative 0.3, and I make one of them negative. We can do that. Now we have an eigenvector. Okay. This doesn't look like something we like to see in statistics because it doesn't sum to 1 and it's not positive. Okay. So again, I jumped from here to get my lambda equals 1 eigenvector. If you want to take your time with it, you can find the null space of this, which is totally fine. Okay, you'll find you'll get the same thing. And what we can go from here is we want it to sum to 100%. So let's divide by what it adds up to. So negative 0.9. Okay, and this will get me 2/3, 1/3. It's my steady state vector. This is the whatever number of people I start with, 2/3 of them will end up in A, and 1/3 of them will end up in B. Okay? So as we go to infinity, we use this here, and this is now equal to 210 times 2/3, 1/3, which gives me 140, 70. And that's how we would solve a problem that looks like this, okay? As time goes to infinity for the system, 140 people are going to be going to restaurant A or drinking soda A or doing whatever, and 70 people are going to be going to restaurant B. Okay? Any questions on this? Do you think you want -60 and -30% in your problem? We want positive percents. I mean, that's fine. It's the same thing. It's fine. You can do it either way. The point of this is me showing the way that you could do it, and it doesn't matter at all. At all. Okay. But yeah, you could make them both positive. That's totally fine. Then you just divide by positive 0.9. You're done. Cool. Questions on this? Yeah. Yep. Yeah. So we know we have an eigenvalue of 1, right? We know that to be true. So what this matrix is here is this is A minus 1i, okay, is what this matrix is, right? So what is the determinant of A minus 1i if 1 is an eigenvalue? 0. That's how we define an eigenvalue, right? An eigenvalue is something that satisfies this to be true. So if its determinant is 0, it is not invertible, and if a 2 by 2 is not invertible, the rows have to be similar. So we don't even have to think about canceling them out. We can just ignore it. Oh, I guess it automatically kicked me out. That sucks. All right, well, y'all have a good night. If you have any other questions, I'll hang out for a minute. Good luck on the exam. I have my office hours tomorrow from 5 to 6. Good luck. And relax a little bit, please. I promise it's not the